All right, welcome. In this video, I want to talk about greedy algorithms, and the way I'm going to do that is by revisiting the job selection problem that we looked at already when we talked about dynamic programming. So we can apply what is called a greedy algorithm to a problem that has what's called the greedy choice property. Greedy choice property is when making a locally optimum choice will lead us to the global optimum, or the optimum that we want at the end. So for instance, if you have a problem where you're trying to end up maximizing the reward, then maybe the locally optimal choice is just always pick the thing, whatever it is, with the biggest reward. And if you do that at the end, you'll have the biggest total reward. And then sometimes similar type of problem might be on the cost side, which is, maybe you're trying to minimize the cost. Well, maybe one way to do that would be always pick the minimum cost thing, the cheapest thing. And then at the end of the day, your total cost will be the cheapest. And this type of property, this greedy choice property, actually occurs in lots of kinds of problems. And in fact, in a lot of those problems, we'll find that the greedy choice, or the locally optimal choice, is actually really easy to come up with. And therefore, a lot of these algorithms seem very, very simple on first glance. Now, when we make a greedy choice, this actually, in a technical sense, is like making a self-reduction. It's a way of reducing the problem down to a subproblem. After we've made this local choice, what remains is something smaller and easier to solve. However, because the greedy algorithms are usually very, very straightforward and simple to state, we don't actually need to frame them in a self-reduction kind of way. And so we usually don't, and often that's just left out. It's an exercise you could go through, but probably not one that's super valuable. One of the reasons is in dynamic programming, we do rely on these self-reductions more, because dynamic programming, one of the reasons we call it dynamic programming, is that choices we make along the way might change as new information comes. That's the dynamism that's in there. That's the changing bit that comes. Whereas in greedy algorithms, we won't ever revisit any choice that we've already made. If we made it and we thought it was good at the time, it will be good later on too, and so we won't have to go back and make those changes. And so that's another reason why we don't need to rely on the self-reduction framework that we do when we're talking about dynamic programming and divide and conquer algorithms. Now, the challenging side that comes then with greedy algorithms is really knowing if the algorithm that you've come up with is correct or not. Now, why is that the challenging side? Well, as I mentioned, the design side can often be very, very easy. Okay, well, just always pick the biggest, or just always pick the smallest, or something like that. Whereas maybe the most difficult thing you're going to have to do is sort your list once you know that you want to take them in that order. And so as a result, it can be very easy to come up with greedy algorithms. And then some of those greedy algorithms that we come up with might not actually be true. And that's the problem that we're going to face when we do greedy algorithms is the algorithm that I'm working on, is it going to be a true algorithm, a correct one, or maybe I've stumbled upon an incorrect algorithm that won't give us the right answer all the time. And that's what we're going to focus on here, is the ability to sort of determine or check, is this solution I've come up with, is this the correct solution or not? And if we want to do that, there's really two ways we can tackle if a problem is correct or not. If it's not correct, what we need to do is we need to show that it's not correct. And the easiest way to do that is just find any input, an example of an input, where if we ran the algorithm, it would not give us the right answer. And usually in this case, that means it would give us some answer, some solution, but it's not optimal. Optimal meaning the minimum or the maximum. And so counterexamples are often considered to be a little bit easier to come up with, because all you need to do is find any one example where the algorithm fails, and then you will have succeeded in showing that the algorithm is not optimal. On the other hand, the other possibility is if, say, we do want to prove it correct, we have sort of an asymmetry here. We can't just prove it correct for one instance. That only allows us to show that that one instance is correct, whereas if we want to show the whole algorithm is correct for all possible inputs, we have to do something more general, and that's where a formal proof of correctness is going to come in. And so what I want to focus on in this first video is our first example of some proofs of correctness that we can prove for a fairly simple or straightforward greedy algorithm. So as I mentioned, I want to revisit the job selection problem. And the job selection problem, as designed normally, is designed to be a dynamic programming problem. And in fact, in our earlier video, we tried maybe a couple of greedy algorithms and showed that they weren't going to be successful. What I'm trying to show here is that by changing the constraint on our job selection problem, we can actually change the type of algorithm that would be best to be deployed for this type of problem. And again, specifically, previously this was a dynamic programming problem, or a problem that has dynamic programming solutions. And now we're going to have a problem that is going to lend itself to greedy solutions. Now, does that mean we can't do a dynamic solution to this? No, we probably could run an algorithm that works very similarly to a dynamic algorithm, but we probably don't need to. This algorithm, in some sense, this problem is going to be simpler than the earlier version. And let's take a look at why that is. What have we changed here? Well, I haven't changed too much. The input is still going to remain the same. Okay, we're going to have just a list of jobs, the payouts for n jobs. There's going to be n jobs. We're going to keep them as positive payouts for now. Okay, we could consider a variant job where there's negatives in there as well. It turns out that's not going to change this problem very much, but it might change it for some of the other variants. And then I've added an extra piece of input here, which is a k. We're going to get some k that's between 0 and n. And then the constraint is dependent on k now. Our output, we're going to get our maximum possible payout just as before, and we're going to get a subset of the jobs just as before. But now the constraint on the set of the jobs is that we're only allowed to select k jobs. And the way this is set up, it's saying I have to select k jobs, exactly k jobs. And then assuming that I've selected out my A to have this size, the k jobs, then if I sum over the payouts for those k jobs, that should be the maximum payout that I can get. So what we've changed is we've changed the constraint from being, okay, if you work on day I, you can't work on the next day or the day before, to a new constraint. And when we're considering this in dynamic programming, we might consider, well, what if we can work 2 days or 1 day, or how, changing the amount of time that we're allowed to take a break on, or how many days we're allowed to work in a row. Those all give us variants that lend to dynamic programming solutions. But changing it, saying, no, it doesn't matter which days you're working. It only matters how many that you're working. They could all be k days in a row, or you could take days off in between. It doesn't matter to us. But you can only work k of them. Then that changes the problem, and it changes the kind of solution. So I want you, hopefully you're already thinking, what kind of solution would be optimal for this problem? How could I solve this one? So I think I've highlighted a little bit of this. We're going to be focusing on how many jobs we can work instead of which jobs. And I also mentioned that this is one that is considered to be a little bit simpler. Because we can deploy a greedy algorithm, which are usually considered to be simpler. So again, think for your second, which jobs should we select to maximize the profit? And this is not a trick problem. So if you're thinking, this seems really easy, it is. Okay, so hopefully whatever you've got in your mind is the right answer. Okay, so the idea should be, well, we should pick the ones that pay us the most. There are k jobs that pay us the most. We should pick those ones and not any other ones. Now, I've left this bit here with a couple questions. Are you certain that selecting the k jobs with the maximum payout will always maximize the total payout? Again, ask yourself for a second, am I certain? I will say I'm certain. And I hope you are too, because this is the kind of thing that it's pretty simple. But you might think to yourself, but wait a second, there's a little bit of a skepticism that I still am holding on to in the back of my head. I believe it is true. But there's got to be some reason we're talking about this. Maybe Chris thinks it's not true and he's going to trick us, and the next slide's going to say, haha, it's not true. So it's okay to have that healthy little bit of skepticism in there. That's what you should always have as a problem solver. Even if you think this is the right answer, you should say, yeah, but can I test this? Or, yeah, but can I prove this? So I do believe, all of us right now hopefully are saying, okay, I'm certain, I do think this is the right one, but we might also be going, but there's a little room for doubt in there, and it would be nice if I could squeeze that doubt out as well, and then maybe move forward. So let's see if we can do that. All right, so to do that, we're going to need a theorem, and a theorem is just a statement of an assertion of some kind of proposition or fact, and usually when we label it a theorem, that means it's something that we're going to try and prove to be true. So in this case, our theorem is going to be, okay, selecting the k jobs with maximum payout. Notice that's kind of a description of the algorithm that we just came up. We said we didn't describe any code or pseudocode, and that's usually because these algorithms are so simple we can describe them in one sentence or even one phrase. And that's what we've got here. One phrase saying selecting the k jobs with maximum payout. That's standing in for saying this is our algorithm. That's what our algorithm would do. And then the next bit, will maximize total payout. That part of the proposition, the assertion, is saying basically it will return the right answer. It will return the correct output. And it might be worthwhile to just go back here and say, well, what is that? Well, that is the maximum possible payout. That's why I used the phrase over here, the maximize the total payout, because we stated in the problem statement that that's what a correct output looks like. So in some ways, we can, this is in a more vague statement of this sentence, we could say our algorithm, because this describes what our algorithm will do, is correct, because this describes what it is to be correct for our problem. But of course, a theorem that says our algorithm is correct is very vague. And our readers, our audience might say, okay, I don't know what you mean. What is your algorithm? What is it correct for? And so it's usually worthwhile to cash that out in a little bit and then explain what you mean. What is our algorithm? Our algorithm is selecting the k jobs with maximum payout. Okay. And then what does it do for us? It's correct, but what does that mean? That means it maximizes the total payout. And this also spells out to us what we're trying to prove, and our audience who's reading, so that they're not surprised by what we're going to do. Now I'm about to present a proof. This proof is an elegant proof, and it is a proof that I came up with, but it didn't flow out of me perfect the first time. In fact, this proof is probably the product of, 15 or 16 drafts of the proof where, I would delicately change one thing, another thing, and so on to get it into this state. Now, why am I saying that? It's so that you, as a reader and a student, as I assume, who's trying to learn how to write these proofs yourself, recognize that this is the finished product, not a early rough draft that we're working on. This is the final state. In the same way that the first time you sit down and write a program, it's not going to be coming out bug-free, but at the end you might have this perfect bug-free implementation. You're looking at the final product here. Okay, now why do I say that? Because I want us to work on our ability to get to this final product, but don't beat yourself up if the first thing that flows out of you doesn't look perfect like this. It probably won't, and it didn't flow out of me looking this way either. Okay, but my first goal in presenting this proof is so that you follow along with me and sort of say, yeah, this I understand now. I understand rather why this proof is going to work, and then hopefully it will dispel that little bit of skepticism that we have in the back of our head, saying, okay, at the end of this proof, we should say, no, that skepticism has no room anymore. I am confident that my algorithm is correct. Okay, let's go ahead and do it. So another thing I'll maybe mention about these proofs is that they do kind of flow like programs, okay? And one thing that's important about them, just like a program, is we usually need to define the things that we want to talk about, and often it's important to give them names, like variable names, and then be very clear about what kind of variable it is and so on. These are just as important in a program as they are in a proof. So this first sentence that I'm really saying here is trying to just set up some definitions. And often this is how we start our proofs, is like, I'm going to call this thing this, and I'm going to call that thing that, and then we can prove that this equals that, or something like that. In this case, what are the things we want to talk about? Well, we want to talk about our algorithm. And our algorithm returns this set of k jobs with the maximum payout. So I'm going to just start out and say, just think about those k jobs with the maximum payout. Let's give them a name. Let's call it, it's a set, so let's call it S for set. And this is our set of k jobs with maximum payout. Now, why do we do this? And why do we give it a name? Well, I give it a name S because I know I'm about to try and do stuff with this set. And I don't want to keep using the informal English of the set, this set, our set, this set, because that's vague and can be confusing to our readers. Instead, we should give our set a name, in this case S, so that whenever we use that specific set down the road, we just say S, and our reader knows, okay, that's S. So I've given this one a name S. And then the next thing I want to do is I want to talk about, and again, why do I go here is, well, we've talked about this first bit now. We've set up a name. We've labeled what the k jobs with maximum payout is. But we haven't said what their total payout is yet. So the next thing I'm going to say is, if we select those K jobs with maximum payout, what would we earn? Well, we would earn this much, where if we take each of the jobs that we selected in S, and we just add up their payout, assuming here we're storing their payouts, not like the name of the job, like working at Burger King or something like that. We name how much money we would earn. Then if we add them all up, that would be the total payout for S. So why are we talking about this? Well, we kind of want to argue that T is maximum. If we can argue that T is maximum, we're done. Okay, that's the goal here. So we've set up S so we can talk about it. We've used S here so we can set up T because we want to talk about that. And now the rest of the proof should be trying to argue that if you had another set other than S, that it should have a sum less than T. Okay, now how are we going to do this? Well, again, we need to be clever when we're coming up proofs. So we need to think about another set. One way we could do this is we could just say, imagine any other set of K jobs. Now, that's one way to do it. I may have actually gone down that route in the past, and I've discovered maybe, oh, it's tangled, or I didn't like this path, or it's got too many steps on it, and I've backtracked and decided I want to take a different path. So instead of just picking any old arbitrary set of size K, I'm going to consider, let's just imagine changing S. Let's imagine if we just make a minor change to S first, okay? Let's imagine we take one of the jobs in S out, and we just replace it with any other job that wasn't in S. And that's sort of the thought experiment I've come up with that I want to push forward to try and see if hopefully this will lead me to a proof. And again, since this is the finished copy, I hope we're all confident that it will lead me to the end. But sometimes these initial steps are missteps, and we will need to backtrack on them. So the next thing I want to do is I want to say, okay, let's do this thought experiment. Consider replacing a job S in S with any other job S prime. I'm giving this one a name now. That's not an S. Okay, now again, notice how having a name for our set S is useful now, because now we can use set notation. And I can say, consider replacing a job S and an element of S. This is very clear to us. That's saying, oh, this is a job that was in our set S, and let's replace it with a different job that's not in our set S. And again, I'm being very conscious of giving these two jobs names so that when I want to talk about them later, I can. Okay. What else do I do here? Well, I've changed this set into this new set. I haven't given the new set name. I guess I could have called it S prime. Okay. I didn't give it a new name because it turns out I didn't need to use that new name anywhere. Maybe I could have used it somewhere, but I didn't. Instead here, what I said is, look, the total sum for our new set is going to be related to the old sum, right? We're going to add up all of the elements that were in S, except remember, what did we do? We took out S, so we'll minus that one off, and we added in our new job S prime, so we added it in. So the new one will have this sum. Now, the next step we want to do is we want to compare these two sums. And we want to know which one's bigger is really what we want to do. Now, if these two sums were just numbers like 70 and 45, then we would just say, look, 70 is bigger than 45, and we would be done. But they're not. They're generalized. They express an algebraic statement. They don't express an actual number because we want it to be general. And so what that means is we need to have some clever way to compare them. We can't just say, look, it's 70 is bigger than 45. We might not know which one of these is bigger. So we need to compare them in a different way. And the way that I want to do it, and a common way we do it when we have an algebraic expression like this, is we subtract one from the other. Because if you subtract one from the other and they're the same, then you get 0. That's a nice special case. If you subtract one from the other and they're not the same, then you either get a positive number or a negative number, and depending on whether it's positive or negative, you will know which one is bigger than the other. And so that's the next technique that I'm going to do, is I'm going to say, let's just imagine if we did t minus t prime. Okay, so what would t minus t prime is? And I'm just pulling down my definition. I said this is what t was, boop. This is what t prime is, bloop. Okay, and then let's do just a little bit of algebra here. Okay, one thing we're going to see here, which is helpful, we got this whole sum and we got this whole sum, and they're about to cancel out with each other, right? So once I've propagated my minus, and I did this very carefully to make sure I flip my signs properly, right? I got a minus of this sum, but this flips to plus and this flips to minus, okay? And then, boom, we're going to cancel out our two sums, and we're just left with s minus s prime. Now, I want to do the rest of the proof, and I know you can follow with me, but if we were just writing this out, we might get to this point, and we might go, well, what is this? What do we know about this? How do we know if there's anything interesting here? Does this get us where we're going? Well, we now need to know something about the relationship between s and s prime. What do we know? Well, we know s was in our set of k jobs with maximum payout, but s prime was not. So we probably know a relationship between s and s prime here. Specifically, since s was among the k jobs with maximum payout, s should have a greater payout than s prime. Although let's be very careful here because there's a very special edge case that we need to consider, which is it's possible that all of our jobs have the exact same payout. And if they do, it doesn't matter which set of k jobs you pick, all sets of k jobs have the same payout. So it's possible that these two jobs have the same payout, remember? Okay, in that case, t minus t prime would be 0 because s minus s prime is 0. Okay, but those are the things we want to consider. We know s is one of the maximal jobs, so s prime can't be bigger than s. That's probably the most important thing that we're picking out here, okay? And kind of what we just did is we just went shuffling through what are the different things we know about s and s prime, and which of those things that we know about s and s prime are probably going to be the most important. And the most important one that we came up with here is s prime cannot be bigger than s. And that allows us to do the next bit of the proof. The next bit of the proof, and basically we're just applying that same reasoning here. We're saying S was among the K jobs with maximum payout, but S prime was not, so we know that S must be greater than or equal to S prime. What does that tell us about this? Then if S is greater than or equal to S prime, this needs to be positive. Okay, so if S, using this, that means S minus S prime must be positive. And since t minus t prime is equal to s minus s prime, it means t minus t prime must be positive. And remember, it's very simple algebra. We can just plus t prime on each side here to see that t then must be greater than or equal to t prime. Let's wind our way back now and say, okay, what are those things? What were we talking about? What's t and t prime? T was the total payout of the k jobs with maximum payout. T prime was the payout of the set that we got when we took one of our jobs out and replaced it with any other job. Okay, we took any job out that was in there and we replaced it with any other job out that was not in there in the first place. This is very general. That's saying it doesn't matter which job you took out and it didn't matter which job you put in. If you just took anyone out and you put any job in, then we know that we may have decreased the total cost, because it could be less than when we get to t prime, or we maybe have kept it the same in the case where the two jobs that we traded had the exact same payout. If the two jobs we traded have the same payout, we're ending up in a case where we're equal, but otherwise we've made things worse. We've got less of a payout. So what this is basically saying is saying, look, take this set that we say you should work, make any swap you want for any other job that you think might be better, and we've shown it's not better. It might be the same, but it's not better. And so that's all we needed to show that our set is the best. There may be others that are equally as good as ours, that's what this is telling us, but none are better. Okay, and so that means that our algorithm selecting the k jobs with maximum payout is correct, and that's good. So hopefully you followed the logic of this proof and you said, well, okay, that makes sense. But maybe there's part of us saying, okay, that makes sense, but it's a little bit clever. Like, where did we come up with this idea of swapping out a job, and how did we know that would work? And part of the answers to that is, how did I come up with that idea? Well, you get some practice and some intuition that you build up through that practice. So there's cleverness here, and with every proof you need to be clever. So at some point you need to go, eureka, there's that idea that I came up with. So that's where it came up. But then with how do I know it's going to work? I don't. That's the key there. I didn't know it was going to work until I got to the bottom, and it worked. Okay, and sometimes when you start trying a path like this, you can get really, really tangled. Maybe the math isn't easy like this; it's awful. Okay, and you might say this is awful, so I want to do something easier. That's why I did the swap argument here instead of just saying pick any other set. I said I only wanted my set to be slightly different. Okay, now we might ask, but have we really compared the set S to every possible other set of size k? Well, the truth is this: every other set of size k can be created through a series of swaps like we've just done here. If we want to make another set, we just need to take one out, put one in, take one out, put one in, and at most we do that k times, and we'll get the new set. And every time we do that, according to this argument, every time we make a set and we do that swap, we are at best making it the same. We're not ever making it better. So that's basically implying that any way you would do this. So, make a swap, make it worse, make another swap, you're not going to make it even better than it was before. It will still be worse. So these are good questions. If you do have those questions, these are good questions to have, because, as I mentioned, this is sort of a final draft of the proof, and it's also a final draft of a proof that is not necessarily intended for computer science students. It's more intended for computer science graduates, ones who have already finished studying it and can look at this and go, yeah, that makes sense, and move on and use it. And part of the reason why I presented it this way is because this is how you're going to find proofs if you go out onto the internet and try and find one. They're usually in this form. That's assuming that you may have already graduated and finished your studies, not in a form that's helping you learn how to do this proof yourself necessarily. So I'm going to pivot now. We're going to look at a different kind of proof after talking a little bit about some properties of proofs of correctness that are important so we can avoid some pitfalls. Okay, so the first thing I want to highlight is, what is a proof of correctness for? Why are we doing it? So here it says a proof of correctness must prove for every input, that's important, that the algorithm produces the correct output. Now, one thing that we can highlight here is that our problem statement tells us exactly what the proper output is for each input. So whenever we're doing a proof of correctness, we are relying on that problem statement very heavily to inform us of what correctness looks like for this problem. Here are some properties of proofs that make the proof, good. They're not always all necessary properties, but they're all properties that we would like to see in our proof. Some of them are necessary. This first one is necessary, which is generality, which is sort of what I was talking about with this for every input, which is our proof must work for every input. Okay, so a common pitfall is to say, well, let's imagine our input looks like this and then show that our algorithm works. Well, all we've actually done is shown that it works for that input, not for all the inputs. And the point of a proof of correctness is to show that it works for all the inputs. And so just showing it works for one input is ineffective or insufficient, because it's even though it might be correct, it's possible you've missed cases where it's incorrect. So the risk here is doing what we sometimes call a proof by example, and that's not a good thing. That's a bad thing. It's a fallacy. That's sometimes also called inappropriate generalization. And I'll show an example of that in a second. Our proof needs to be universal. Not all proofs need to be universal, but ours does, which is saying that our solution needs to be shown to be better than all other solutions, not just some of the other solutions, but all of the other solutions. And we should also be careful to note here that it doesn't have to be strictly better. I put that here. It could be equal to some of the other possible alternatives. And maybe this is a good point to highlight that not every optimization problem is going to have a unique solution, one specific optimum, one specific maximum or minimum. It's possible that there are multiple maximums or minimums, in which case any is usually an acceptable answer, but it impacts how we're going to do our proof of correctness, because just because we've come up with a correct solution doesn't mean that some other algorithm might not come up with a different correct solution, which is something we should be aware of. This is another possible risk of falling into proof by example, although this type of proof by example is a little bit more subtle, because you don't just set up and say, I'm only trying this one case. You set it up to try and be general, but maybe you miss out a category of cases that are important, and so it's important for us to be rigorous in our case selection. Okay, one example of that is sometimes our cases, maybe we have two integers a and b, and then we might say, well, what's the relationship between a and b? What are the cases? Well, a could be less than b, a could be greater than b, a could be equal to b. Those are three cases. Or we might just say a is equal to b and a is not equal to b. Those are two cases. But however we set up our case structure, we want to make sure that it is exhaustive. It covers all of the cases. And that in that case, we will have a universal proof. We want our proof to also be what's considered complete, meaning all of the important information that needs to be brought to bear should be in our argument. If there's any information that's left out, this is a possibility where we could be making an error. We might be leaving out information that's false, and in which case that jeopardizes our proof. But it also might just make it so our reader is unclear of where we're going. We may be not able to follow, or your reader might not be able to follow your path because you're skipping over steps. Now, this one is definitely a desired property of proofs of correctness, but unfortunately it comes with a trade-off, which is if you were going to put all the relevant information into your argument, you would be proving everything all the way down to base principles, things like 1 + 1 = 2. We don't have time to include all that in there, and it actually jeopardizes our readers' ability to understand our material when we're bogging them down with very, very basic information. So while we want to make sure that our proofs are complete and include all relevant information, there is a trade-off there, which is some information is details that our reader could easily fill in and probably doesn't need us to re-mention. Okay, so our risk on this one is doing something called begging the question. And I'm going to show an example of that, and you may have seen that before. Begging the question is another logical fallacy that occurs when you assume what you're trying to prove, in which case you could prove anything, because you can prove anything by assuming that it is true. This is where some of our trade-offs are going to come in. We want to be precise. Precise meaning in the precision case, what it means is we want to make sure that the language that we're using is, one, correct, and then two, not vague. Sometimes when we don't know what the correct language is, we are tempted to be vague so that we are not incorrect, but both are not going to be good if what we're trying to do is do a proof, because our reader needs to know exactly what we're saying. And so if you're tempted to use some vague language, you're probably in a case where you're not as certain about what you're trying to say. And so that's a good point to stop and say, okay, what is it exactly that I'm trying to say? And then maybe reevaluate, is what I'm trying to say even correct? Because it might be false. Our risk in this case is doing something called equivocation, which it's commonly described as doing something where you use the vague language to cover up some uncertainty that you might have, and sometimes that's not conscious, you just do it naturally, but it also can be done deliberately when you intentionally use the wrong words to convey a mistaken information or misinformation, so that your reader can be confused and follow you down maybe your incorrect proof. And of course, it's not good to do this on purpose, but hopefully none of us are doing that. But it is a good idea to be aware of this risk, because we do sometimes naturally fall into equivocating, like I said, when we're not certain about what the proper language to use is. And so if you feel yourself starting to just use vague language, then you may be in this case. Sit down, go review your definitions, make sure you're using the words the way you intend them. Okay, here's the last one. This one definitely pulls in the other direction of completeness, which is being concise. Concise means not including any more information that is necessary. So in some sense, these two are not really in contention, because here I'm saying all the relevant, and here I'm saying only the ones that are necessary. Well, hopefully all the relevant information is necessary, and all the necessary information is relevant, and this is the same set. But all of this is very subjective. Necessary for what? Relevant to whom? Right? And so here is where there's definitely some back and forth. Should I skip this step or should I fill it in? And definitely when I'm proving my proofs here, even in this video, I have very deliberately asked myself, should I leave this in? Will my students be able to fill this in? And at specific cases, I go back and forth sometimes, and I'm like, oh, I want to delete that. Oh, I need to leave it in. Oh, I want to delete that. And it's okay if you're feeling that same temptation, because that probably means you're in the sweet spot. You're in that right spot for treating your audience with respect, respecting their intellect, but also giving them all the information that they do need to understand your proof. Okay, and again, I'm going to try and highlight some of these properties as we go through a couple more examples of proofs. What's the risk of, in this case? Well, sometimes there's a risk in writing a proof to add in extra information that is not even relevant. And that's not really risky. It's just kind of meandering, which is your readers are trying to follow your logical path, and then you go on a tangent about something that's irrelevant. That's just inviting them to be confused, okay? And then the other risk of this is then maybe your tangent, you go and say something false. And that can jeopardize your proof, not because your proof is not correct, but because now your audience is not going to believe your proof. They're reading your proof, blah, 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 and you get to some point and it says 1 + 1 = 3. Even if that's not relevant to the proof, they're going to say, what does this person know? They think 1 + 1 = 3, so how should I believe the rest of this proof? So, it's important to weed out irrelevant statements, partly because those irrelevant statements may jeopardize your audience's ability to digest your proof in the way it's intended. Okay, so all of these constraints on a proof mean that writing a proof is not a science, it's more of an art, and you'll get better at it. So it's just like actually writing a program is kind of artistic, and also writing, an essay. You get better at it over time, and you also want to do multiple drafts to make sure that it's good. Every time you're doing a draft, you're assessing your points for logical consistency and making sure you're using those definitions appropriately. Okay. It's also important when we're writing our proof, I think I hit on this a couple times, to consider your intended audience. Now, on the internet, most people's intended audience when they are writing proofs of correctness are other computer scientists in the industry, already in the trade, already practicing maybe for a handful of years or even decades, meaning they assume certain things about that audience that you're comfortable filling in certain steps on your own, probably because you've read a dozen of these proofs before, and so you're already pretty comfortable with them. I don't assume that's true necessarily of all my students, since they're still studying, and this may have been the first proof that you've ever looked at, proof of correctness that is, in which case I want to ease you into it a little bit more. And you as students, I recommend when you're writing your own proofs, do the same thing. Treat your fellow students as your intended audience. Don't assume that they know everything altogether. Do assume they know basic arithmetic. You don't need to fill in, 1 + 1 = 2, that kind of stuff. But maybe fill in a little bit of set theory here, or maybe draw attention to the particular algebraic rule you're applying here, and so on, because they may have forgotten it and may have forgotten how it works, just like you may have forgotten some in your own studies. And so I'll just reiterate what I've already said. The last proof I wrote it as though I was just trying to write the most elegant, perfect proof of correctness I could imagine. And that usually means my audience is, not students, they're graduates. And so what it means is some parts have been, the way I put it here is I said some parts have been left out. Now, are those necessary parts that have been left out? The answer to that is necessary for whom? Necessary for students, then yes, I have left out some parts that are probably necessary for my students to understand. Necessary for another, researcher in the industry to understand? No, they probably would have followed my proof and said, yep, that looks good to me. So let's try and fill in a little bit of those extra bits. Actually, I've got a few things I want to do before that. So before we do that, let's look at a couple of these pitfalls that we can get into when we're trying to write one of these proofs, and then we maybe take a misstep. The first one here is a fallacy called begging the question. Now let me remind you what a fallacy is. A fallacy is a logical error or an error in reasoning. And it's common for us to make these errors in reasoning. Luckily, human beings are actually incredibly efficient logicians or reasoners. Our built-in brain is really, really good at doing logic. Except there's just a few little, trick-ups where our brain is tempted to go down the wrong path and make the wrong inference. And so we call these fallacies, and we highlight them so that you can be aware of them so you don't want to do them. Okay. One of them is begging the question, which is, as I've said here, assuming what you are trying to prove. So let me give you a quick example. Here's something I just pulled from the internet. Everyone likes Tom Hanks because he is just so likable. Now, I don't know if that's true or not, because while I like some of Tom Hanks' movies, I wouldn't say I'm a big fan of his. So if someone came to me and said, everyone likes Tom Hanks, and I said, really? Why? If they came back and said, because he's just so likable, I don't think I'd be very convinced by that. In fact, I might just say, you haven't actually told me anything. And in fact, what I've sort of got here is we could rephrase this by saying, everyone likes Tom Hanks because everyone likes Tom Hanks, which does not add any information. That's part of the key bit. Nor does it help us understand why everyone likes Tom Hanks. It just repeats that everyone likes Tom Hanks. So this is a good example, a little one-sentence example of begging the question. And we do this a lot in natural language. A lot of times we'll do that. And a lot of times we let people get away with it because it just doesn't matter why everyone likes Tom Hanks. I'm okay with this. But in math, it does usually matter. So the next question might be, well, why is this bad? Sometimes it's okay. As far as Tom Hanks is concerned, that's probably fine. But the problem is, if we're considering this as an actual formal proof, we can prove anything we want. So for instance, consider these two proofs I've got here. 1 plus 1 is 3 because 3 is equal to 1 plus 1. Or 1 plus 1 is 2 because 2 is equal to 1 plus 1. Now, we all know what 1 plus 1 is, so we know that the second one is true and the first one is false. But there's nothing about the proof of the second one that should make us believe the second one over the first one. They both are proving things in the exact same way. And if we believe the second proof, we should believe the first proof too, because it's the exact same structure. And so that's what we take away here. Both of these are begging the question, so they're both bad proofs. So we shouldn't trust either of them. Even the one that's true, even the one that happens to be true, we shouldn't believe it. We know it's true for other reasons, but we shouldn't believe this proof. We should say, yeah, you got lucky, but you didn't prove it to anyone. Okay, and let's see if we can see an example of that with our current task at hand. So say we want to prove our theorem, selecting the K jobs with maximum payout will maximize total payout. Here's my proof, the begging the question proof. So I should have a big strike through this saying, this is bad, don't do it. It says, but we're very tempted as students, but even as researchers, to do stuff like this. If we select any other jobs, the total sum will not be greater, or will be less, is usually what we're tempted to say, but that would technically be false. But effectively what we're saying here is kind of a well, duh, where we're not trying to prove the theorem. We're really just kicking it back to our audience and saying, come on, you believe this, right? And you must already believe this, and we don't need a proof, right? So let's just back away and not try and prove it. And we're tempted to do that because it's easier. It's very easy to beg the question, but we should fight that temptation to beg the question. And so it's rare that we do it this simply, but sometimes we'll set up our proof, and then as soon as we need to be clever, we'll just say, and it's the best because it's the best, and then we move on. And if I see that in some of your work, I'll make sure I flag it and highlight and say, hey, we need a better justification here. So again, while the statement here if we select any other jobs, the sum will not be greater. This is indeed true. But even though it's true, it fails to prove the theorem because we haven't added any information and no one will believe us if they didn't already believe us. If they already believed us, we don't need a proof. If they didn't already believe us, this is not sufficient. Okay, so another fallacy that I want us to avoid is one called proof by example or inappropriate generalization, where we try to prove a generalization, a for all. This is true for all things by just citing one instance of it and just saying it must be true for all of them because it's true for this one. So here's the example that I pulled out again. I know a corrupt politician, so all politicians must be corrupt. So I place here, because I understand logic, that it's possible that not all politicians are corrupt. I say that because I'm not sure if it's true, but it is possible that not all politicians are corrupt, so we should not believe this proof. So I don't believe this proof, even though I know a corrupt politician or two. I'm not going to immediately jump to the conclusion that all politicians are corrupt. I'll wait for evidence on the other ones because that's innocent until proven guilty, at least in the countries that I'm from. What can we infer from this knowledge? If I do know a corrupt politician, I don't know all of them are corrupt, but it does mean some of them are corrupt. And in fact, what we're doing here is we're making a mistake. We're applying a universal quantifier, a for all, when what we should be doing is an existential, there exists. And that's the error, the fallacy we're making here. So again, why is this bad? Well, we can prove things that are false. Usually fallacies are bad because we can prove things that are false. And in this case, we can prove things that are false as long as there's one instance that's true. So imagine this very silly theorem. The sum of any two numbers is 7. Okay, x plus y equals 7 for all x and all y. Here's my proof. See? Imagine x is 4 and imagine y is 3 and 4 plus 3 is 7. There you go, proof done. Well, hopefully you're like, well, of course that's not true. I can prove it immediately by just picking two other numbers probably. Almost any other two numbers you pick will not add up to 7 and you will say, see, you're false. Okay, so luckily this type of error can be usually disproved quite easily. Another simple one, all the integers are 0 because 0 is an integer. Obviously not true. Okay, and I think I already mentioned this. Applying universal quantifier instead of an existential quantifier, this is the error that we're doing. Okay, how might it play out in our proof of correctness now? Well, again, I've got my theorem set up here. Well, here's where we say, look, I don't want to do the general part. I don't want to assume I have any input. I just want to say, assume I have this input. Assume the jobs that I have pay out $4, $5, and $6, and that I'm only allowed to pick 2 of them. Then look at all the possible solutions. We could pick 4 and 5. We could pick 4 and 6. We could pick 5 and 6. The last one is the one with maximum payout, right? We can just inspect them and know that that's true. And it has a total payout of 11. Whereas the other two have total payout 9 and 10. Again, you can go and check it yourself if you need to, but all the information's here, which are obviously less. 9 and 10 is obviously less than 11. So our algorithm is correct on this instance. The problem is we've only shown it's correct for this instance. And we don't know if we're in the same case as this 4 plus 3 equals 7 business. Maybe, you just cherry picked the exact instance that your algorithm works for, the one it works for out of the infinite inputs. And then how do we know that it doesn't fail on all the rest? Now, it turns out our algorithm is correct. So it doesn't fail on all the other ones. So in some sense, why not believe this? Well, why not believe this? Because we can't tell it apart from this up above. Okay, so we have to still go back and push back on the prover here and say, look, I believe you on this instance, but what about other ones? What if n is bigger than 3? What if k is bigger than 2? What if we have different values in the set? How do we know it's going to work for those ones too? And luckily, this is not a complete failure. Okay, it's not a complete failure because if you started out this way, and your friend or whoever you're working with says, look, but we need to try the other ones. What if n is greater than 3? What if, and so on. Try those other ones too. You're never going to get a complete proof by just gluing together a bunch of examples, But every new example you try will inform you better about why this algorithm works correctly and might help you come up with the actual proof, the more general proof that you're aiming at. So it's okay to try out instances like this and try and figure out why it works, but they never amount to a complete proof at the end of the day. Okay, again, while this entire proof here doesn't say anything false, again, it fails to prove the theorem. So we shouldn't believe it. And that's because it doesn't cover all the possible inputs. It only covers this one. All right, now let's take a look at a more rigorous proof where what we're going to do is use a little bit more framework around the proof. It's going to be effectively the same proof. When we get to the clever part where the math is going to kick in and we're going to need to do some actual comparisons of one set to another, it's going to be the exact same argument. And so in this sense, I call that sometimes the clever piece. The clever piece is always going to be the piece that you need to work the hardest to think about. It's also the most important piece of the proof, but sometimes it's easier to work on that clever piece when we set up the framework around it so we can better see what it is that we're trying to prove. Okay, so now I'm going to set up this proof a little bit different than the last one. I'm going to set it up with a couple of the pieces that I left out before. Part of the reason I left it out before is because, again, remember, if I assume my audience is a bunch of researchers that have already, read these types of proof before, they're going to know this by it, and they're not going to need it. But we're students, so let's look at this. First one is setting up our generality. This is where we're making sure we're not doing a proof by example. Because if we're doing a proof by example on this statement, what we would like to say is assume our input looks like this. But instead what we're going to say here is no, assume we have any old input whatsoever. So here I'm saying assume the input is n jobs. Which n jobs? I haven't said. What is n? I haven't said. Okay. And that we get a k. The only thing I'm saying about the k here is that it's in the appropriate range because the input of the problem already told us that's the k that we should get. Okay. And I've also assumed that all the payouts are arbitrary. So I don't know what n is, I don't know what the payouts are, and I don't know what k is. This is any input. What that means is the proof that I'm about to set up will apply to any input, and that's the generality bit. Next thing I'm going to do, I'm going to want to set it up by giving me something to talk about. Just like before, I set up this S. I'm going to do it again, but slightly more deliberate. So now, again, I'm going to say let S be the set of k jobs with maximum payout. But now I want another, I'm going to pick another solution out. Now, here's a bit where I want us to think that in the mathematical world, and don't think about the algorithm that creates this output for a second. Just think about the fact that this output exists. We know there is some output that maximizes the total payout. We don't know what it is yet. We hope it's S. In fact, we're trying to prove it's S. Okay? But for the moment, I'm just going to say, let's assume we know there's some set of k jobs that maximize the total payout. Let's go and grab them. Let's get the set of k jobs that has the maximum total payout, and let's give it a name. I'm going to call it O. Now, it's possible that what we've done here, in fact, if we're successful, what we've done here is we've given two names to the same thing. S is the k jobs with maximum payout. O are the k jobs that maximize the total payout. But if our proof is correct, those are the same thing. So hopefully these are the same thing. And in fact, that's what our proof is trying to do. We want to show that these are the same thing. If we show they're the same thing, we're done. And in fact, that's the next thing I'm going to say is, look, if these are the same thing, we're done. Okay, so at this point we're saying if S is equal to O, we know that S has the maximum total payout and we've proven our theorem. So why do I even make this statement? This is another statement that is very, very often left out because everyone knows this. If it already is optimal, then it's optimal. So the way the proof moves on from here is we need to assume they're not equal. We need to say, assume S is not equal to O, and then see what happens. And sometimes when we make this assumption, we'll get to a contradiction. which is good because that means that this assumption is false and couldn't possibly have ever been true. But then other times we get to a special case where we have to say, actually, this is possible. It is possible that S is not equal to O. And remember, when does that case show up? When we don't have a unique solution. Okay, in our problem here, when do we not have a unique solution? Remember, if all the jobs pay the exact same thing, it doesn't matter which jobs you pick, just pick K, any K jobs. So always keep that kind of problem in the back of your mind to say, well, is it possible that there's more than one unique solution? Is it possible that S is not equal to O and we still have an optimal solution in S? And the answer usually is yes. And we'll get to that here in a second too. Okay, so as I mentioned, I'm setting it up. The next step is assume S is not equal to O. Okay, now that they're not equal, that means there's something different about them, right? We could characterize that more strictly, like there's a job that's in S that's not in O, or vice versa. There's a job that's in O that's not in S. And that's what we want to focus on. We want to go down and figure out these jobs. And remember our old proof? Our old proof did a swap. It said, what happens if we switch these two jobs out? We're trying to get to that same kind of structure here, okay? We're trying to say, look, there's probably some place they're different. Let's go and look at that place where they're different, because that's where we're going to see that their total sum might be different as well, okay? So we need to, again, we're setting up definitions of variables so that when we use them, they're very explicit and our reader knows what they mean. So the next thing I'm going to say here is say, let's assume that I is the first job where S selects SI and O selects something different, OI, not equal to SI. And here I said first job, and I need to backtrack up because I skipped over a little bit on this last sentence. I didn't just say assume they're not equal to each other. I also said, well, now let's start comparing their jobs one at a time. Which jobs? In what order? Okay. Well, to make sure we're comparing them the same jobs to the same jobs, I've decided to put them in decreasing order of their payout. Why decreasing order? Well, and you might think, why not increasing or something else? Well, the reason I've picked decreasing order, that's the order that I imagine my algorithm would have selected my jobs. First, it would pick out the maximum and say, I'm working that one. Then it would pick the next maximum and say, I would work that one. So I want it to be in the order that I imagine my algorithm works. Now, how does the algorithm for O work? We don't know. Okay. So in this sense, we're saying, I don't know what order you picked them out, O, but can you please put your jobs in the same order as us so we can compare them one at a time? Now imagine the maximum job is selected by both S and O. Okay, so then that means the first job when we're comparing one by one in decreasing order are the same. So we want I to be the first job where they're not the same. So maybe it's the first job, maybe it's the second job, maybe it's some job later on. Let's just call that the ith job. Okay, and once we've got to that point, we now know O picked a different job than we did. Okay. Let's keep going because there's some subtleties here that I want to pull out, and we need to dig down into this example to really see what's going on here. Okay, so let's go to the first bit here, which is what do we know about S and what do we know about O? That will help us make some argument about OI and SI. Okay, so what do we know about S again? S is the set of K jobs with maximum payout. So if S has picked a job and O has not picked that job, then that means O has not picked one of the jobs with maximum payout. Okay. The other thing we're noticing here, and this is getting back to this choice to put them in decreasing order of payout, since we're considering jobs in decreasing order of payout, we know that we have looked at the maximum job first and they agreed, or let's assume they agreed. And then we looked at the next one and maybe they agreed too. And eventually we got to job I and they disagreed. Well, we know at this point S is picking the maximum job it can. And if O is picking a job other than that, there's nothing bigger that it could have picked. We've already agreed on all the ones that are bigger. So the only thing that O could pick is a job that is less than or equal to SI. Okay, possibly equal to. Remember, we want to keep that possibility in the back of our mind, but the job must be less than or equal to the job selected by S. Here's another important and subtle observation. Okay, since O is in decreasing order of payout, we know that O can't just pick SI later on. If it was going to pick SI, it has to do it right now, because we've put them in decreasing order of payout. And since SI is not appearing now, we know it's not going to be appearing later on in O. So it is not selected by O. Okay, so we're going to assume here SI is not selected by O in this step. What does that mean? That means we can go grab SI and put it back in O. Okay, now the problem is if we go grab SI and put it back in O, we now have K plus 1 jobs. So we need to take a job out. Which job should we take out? I don't know. How about OI? Okay, we'll kick out OI and we'll put SI in instead. Okay, and we'll call the new set that we get out of this O prime. Now, we might ask ourselves, why would we ever do this? What's the point of doing this? Well, there's two possible reasons we might want to do this. The first reason is, hopefully, making this change makes O better. Okay, and the idea that we think that you should pick SI, and you didn't. You picked OI instead. And let's consider the case where OI is strictly less than SI. Then that means you made a mistake. You should have picked SI instead, you would have got a bigger sum. So we want to go and look at O prime now because we want to say, look, O prime has a bigger sum, which is good because if O prime has a bigger sum, that means we've got that contradiction. What contradiction? Well, remember we assumed up here O is optimal. O has the biggest possible sum. It already has the maximum possible payout. If we can show there's another set that has a bigger payout, that's a contradiction. Okay, so that's one of the branches we might go down. The other possibility, though, might be, what if our two jobs had the exact same cost or the exact same reward? If that's the case, then O and O prime will have the same payout. And that is important to us as well because it means O prime is still optimal. If O is optimal, then O prime will be optimal if it has the same payout. But what's special about O prime now? It has SI. It picks SI and not OI. Okay, it picks the same one that we pick. And because of that, well, we'll see in a second, it will allow our proof to move forward. Let's see how we're going to deploy this idea now. Okay, so after this replacement, so remember we said take one out, put one in. Why did we do that? So that we can make sure that the size of the new set is still K. Remember, we're only allowed to select sets of size K. So if this didn't have K jobs in it, it would end up being not a valid solution. And I'll say a few more things about validity in a bit. Not a valid solution, meaning we wouldn't even accept it as a solution, so we shouldn't consider it here. But it is a valid solution because it does still have K jobs, so we should consider it. We might want to look at what its payout is. Okay. Well, what is its payout? Well, let's go and do the same thing we did in our previous proof. Let's go and define these terms, T and T prime. And there, I've used a slightly different sum, but it's the same idea. Add up all of the O's in O, or all the O's in O prime, and those will just give us two different payouts, T and T prime. Okay. So if we wanted, we can set up same reasoning before. T minus T prime is going to allow us to compare those two totals and figure out which one is bigger. So we're going to take O, and we're going to minus off O prime here. Now you'll notice these sums look a little bit different. I didn't have the plus S minus S prime kind of business in there, but that same business is going on. There is still a plus SI and a minus OI or something like that. We've just got SIs and OIs now. Okay. Now let's be careful and make sure we're doing this right. Okay. O is the optimal solution. It picks OI. That's what we assumed up here, right? O selects OI. O prime is the one where we took out OI and we put SI back in. Now all the other terms in this sum and this sum are exactly the same. So when we do this minus, they all cancel out. So we actually end up with only two terms. The one that pops out of here is OI, and the one that pops out of here is SI because we took OI out and we put SI in. And so we end up with OI minus SI. Now remember, in our previous proof, we ended up with S minus S prime. This is the same. We've ended up in the same case here, okay? The only interesting difference here is we've kind of got things a little bit backwards. Not backwards for the purpose of our proof, but just in the opposite order as we had in our previous proof. Because what do we know? We know that SI is greater than or equal to OI, which means OI minus SI must be less than or equal to 0, okay? And that's that next little bit here, okay? So since we know this relationship between SI and OI, we know that their sum must be less than or equal to 0. That means that this difference must be less than or equal to 0 as well. And now that means that t is less than or equal to t prime. Opposite relationship we saw in our previous proof, but that's the proof that we kind of want to get. There's two branches on this proof. One is, what if it's less than? If it's strictly less than, this is what I was saying earlier, we have found a more optimal solution than O, which is a contradiction. It contradicts our assumption that O was optimal. And remember, when we get a contradiction, that means this branch is impossible. So it's impossible for us to get here with t less than t prime. So it means they must be equal. So t must be equal to t prime. If t must be equal to t prime, it means si must be equal to oi. So those two are the same. And in this case, what was the argument we wanted to deploy in this case? In this case, O prime is still optimal because it has the same payout as O. But now it selects the same job as S, at least at this point. It selects the job S prime. So there's actually going to be a little bit of induction going on here. So I want you to come back with me because it's hidden induction. I sometimes call this pseudo-induction, where we can jump all the way back to the beginning now and say, well, remember here where we said let O be an optimal set of K jobs that has the maximum total payout? It says an optimal set. Imagine at the beginning, if instead of picking the O we picked at the beginning, we picked O prime, because O prime is also an optimal set, right? So when we have more than one optimal set, we don't know which one we picked. Maybe we picked the wrong one. So we pick O prime instead, start the proof all over again, go working through. When we get to point I, they now agree. Okay, so when we get to point I, they now agree, we keep moving. There's two possibilities. Maybe after this swap at O prime, they're equal now. So we get all the way to the end, we don't have to make any argument. Or it's possible that we get to a new I later on, maybe we'll call it J. J, where there's another difference. Well, we can apply this exact same argument again, saying, well, do a swap and get, maybe call it O double prime now, and now we'll agree on point J as well. And so this induction is going to kick in and say, it doesn't matter. Every single point where you disagree, you can make this same argument, so we must agree on all the points. Okay, so that's this last little bit that I'm going to put in here. If O prime still differs from S after this change, we just repeat this argument, ensuring that there is an optimal solution. There is an optimal solution that selects the same jobs as S. So again, we're not saying here S is the one and only optimal solution. We are saying S is equal to an optimal solution, and there might be other ones that it's not equal to. Equal to in terms of its organization, but not in terms of its total payout. And that actually is just going to complete the proof. And to complete this proof, I just wanted to add this sort of what I sometimes call a post-annable, just a finishing up saying, hey, look, we actually did what we were trying to do. All right, so in that last proof, we looked at it and I said there's a little bit of hidden induction in behind there. That's because another common way that we can prove this is doing induction. Now, I absolutely hate this way of doing it because it's just a lot of tedious work, but I'm going to present another example of it just so we can see our third example of proving the same theorem, this time with induction. If you're a student and you're trying to work on proofs, unless you've got that really analytical brain and you just think induction is really cool, it is kind of cool, then I wouldn't recommend using this technique. I would recommend using one of the other two techniques that we just looked at. In fact, I would recommend using the last one we looked at, and then after you're comfortable with it, trying to tackle the more concise version that we looked at first. Okay, let's do this last bit here where we're going to look at a proof by induction. And I'm going to do it a little bit strange here. I'm going to do proof by induction on K, how many jobs we're allowed to select. Okay, not on N, how many jobs we're allowed to pick from. It's possible you could do it on N as well, although I haven't tried that. I think it might be a more difficult proof to make. In which case, I'm just going to do it on K. So what's the beginning then? What's our base? Remember how induction works is that we start with a base case, then we make a hypothesis, and then we use that hypothesis to prove our inductive case. So I'm starting out this proof in the same way as the last one, starting to make sure we're general with an arbitrary input. But now I'm going to say, let's do some induction. Okay, induction K, my base case, I'm going to pick K equals 0. This is trivial. if we're going to select 0 jobs, then the maximum payout is 0, and that is achieved by selecting the empty set or no jobs. So that's trivial, straightforward, and again, maybe one reason why a lot of folks don't use the formal induction on this is almost always the base case is an n equals 0 or k equals 0 kind of case, and always the solution to the empty case is 0 or the empty set or the something. It's just always very, very super trivial that even if you were to see sort of an inductive proof of this, they would leave this bit out saying this is a trivial base case. Likewise, with the inductive hypothesis, we would get to the inductive hypothesis here and say, anyone who knows induction can fill this in themselves, and so we don't need to explicitly state it. Okay, and so all I've really done is restated what I'm trying to prove here. This looks like I'm begging the question, but if you are familiar with how induction works, especially weak induction, which is what I'm doing here, we're going to assume it for a specific k. Not all the k's, and then we're going to show that it is true for the next k, which with the power of induction will then show it's true for all the k's. So again, this is straightforward. We're probably just going to leave it out if we were, if we're writing for an audience of non-students. Okay, so now we're going to look at the inductive case where, as I've sort of hinted already, we need to show that this is going to be true for the k+1 jobs. Okay, so now we're saying, imagine that we've switched the instance to a case where now we need to select k+1 jobs, and we want to make sure that our algorithm is still going to give us the appropriate output, maximize the total payout. So to do this, I'm going to try and do the exact same reasoning that we've just done twice in our 2 previous proofs. The first is I only want to consider adding one extra job. One extra job to what? Well, to a set of k jobs that, thanks to our inductive hypothesis, we will know is already optimal. Okay, so for instance, the way I'm going to describe that is, say we're looking at our instance, okay, and let's say we pick out the k+1 jobs with maximum payout. Well, those k+1 jobs with maximum payout also contain the set S of k jobs with maximum payout. So I'm giving it the name right now, S. I haven't named it yet, nowhere up above. So here I'm actually labeling it. I'm saying, let's name the set S of the k jobs with maximum payout, or let's give that the name S, and then we'll note that the k+1 jobs with maximum payout includes that set. It includes that set S plus one other job. Okay. Here's where we're going to apply the inductive hypothesis. We know that S maximizes total payout over all sets of k jobs. That's the inductive hypothesis. So we don't need to consider adding any jobs to any other sets other than S. There may be other sets of k jobs that have an equal total of S, but then they will have an equal total afterwards. So we're only going to have to consider adding a new element to the set S. Okay, and we'll just consider which element should we add. So all the jobs that are not already in S, one of them has the maximum payout, and I want to give that one a name, so let's call it S. That's the job that the k+1 jobs with maximum payout will include. So that's what we say next. So the set of k+1 jobs with maximum payout is S union this extra job. Okay, we say, well, consider any other set of k+1 jobs, S union O, where O is just some other job that's not S, but is also not already in S. Okay, so basically we're saying here, we're setting it up for our comparison. We're saying our algorithm will pick S and put it in. So let's just imagine any other algorithm out there might pick some other job O and put it in. And we want to compare those two. And again, our goal is the same. We want to show ours is the best. So again, we're going to set up two formulas for the total payouts. We've got a sum here. Notice again, slightly changed. I'm using A's now. I've got S union S and S union O as my two sets, not an S and an S prime, but they're effectively the same thing. We've just got slightly different names for them. Okay, tell me if you recognize this math. Okay, so one of them's got a plus S, one of them's got a plus O, but then after some canceling out of the A's, we get an S minus O. Okay, so hopefully we don't need to review this part. This is what I'm saying. The clever piece of all these proofs is going to be the same, even though some of the machinery around the outside could be different. Okay, and then again, we're going to try and make this argument now. What do we know? Okay, well, S was the job in, the job not in S with maximum payout, and O was any other job. So since S was the one with maximum payout, we know, again, same relationship we saw before, S is greater than or equal to O. Okay, what does that tell us about this difference then? Well, it must be greater than 0. And if it's greater than 0, the difference between our two sums must be greater than 0, implying what? That T, this sum, oh good, that's the one with S in it, must be greater than or equal to this one, the one with O in it. Well, that's what we were trying to argue. Okay, so the total payout of S union S is greater than or equal to the total payout of any other set of k plus 1 jobs, and that finishes our inductive proof for us. Okay, again, I went through that one a little bit quicker, hopefully because it's pretty clear, but also because we've done this sort of clever piece. This is our third time now. And again, I just want to highlight that while this is an acceptable proof of correctness for this problem as well, I rarely invoke actual induction in my proofs, and instead I like that sort of second proof I did where we've got induction going on kind of in the background behind the scenes, but we don't need to actually draw attention to it for our readers because it's not super relevant, and it might just bog them down with irrelevant details that might not help them understand. So well, thanks a lot for watching this video. This is intended to be an introduction to some greedy algorithms and proofs of correctness. And in my next couple videos, we're going to dive right in and try proofs of correctness of a few other problems and a few other algorithms very similar to this. So thanks a lot for watching, and we'll see you in that next video.